Let's start today's discussion. Good evening, everyone. Uh, Myself, Moma Samanto, is research scholar from IIT Kharagpur, and I am your tutor. I mean teaching assistant for this course, Algebraic Number Theory. For this starting from this July 2026, and the course instructor is Professor Sripad Garg from IIT Bombay. So this is our week 2 tutorial session, and let's start with our today's discussion. Okay, so today's so before starting, I would like to know if you have any doubt from the courses, from the lectures which is taught by Professor Sripad Garg. Do you have any doubt from those lectures? If you have any, then you can tell me now. Then I will try to solve these fast. Then I will try to solve some problems which are related to the topic of week 2. So before starting those problems, I would like to know if you have any particular doubt in any lectures or in any assignments. You can tell me, and first start with that. After that I will solve some questions. If you don't have any doubt, just say no, then I will proceed further. Okay, so Jose, you don't have any problem till now. Others? Okay, so if you don't have any problem, so let's start solving some questions today. So first I would like to tell you the outline of today's tutorial session. So first, in our week 1 discussion, I have discussed up to the principle of mathematical induction. So I would complete the rest portions from week 1 video, week 1 lectures, and then we will go to the week 2 lectures. Okay, so I would like to solve this topic, some problems on this topic. So first we will see some observations from, or you can say on division algorithm. Then we will solve some problems on divisibility, and GCD. These are the two topics which are covered in week 1 lectures. Okay, and then we will go some problems with prime numbers and fundamental theorem of arithmetic. And then we will go theory of or congruence relation. So from these topics we will try some problems. Okay, so what is our plan today? Some we will see some observations on division algorithm. Then we will discuss some problems from divisibility and GCD from this portion, and then we will go to the pro with some problems from prime numbers and fundamental theorem of arithmetic, and then at last we will solve some questions on congruence relations. So I hope you have seen the all the lectures up to week 2. Yes, right? So if you didn't see till now, then you can just go and see all the lectures, because I will try to cover some problems based on those lectures. Okay, so let's start with division algorithm. So first recall what was the statement we have seen in our lectures from division algorithm. So what was the statement of division algorithm? Can anyone tell me? Just turn on your mic and you can just tell me.
Ma'am, if A and B are any natural numbers, B is not 0,
So
then B divides and
A and B belongs to natural numbers, and
B is not 0.
B not equals to 0. Then
There exist unique Q and R which belong to natural numbers.
then there exists unique Q and R. Sorry, Q and R in N, such that what is the relation?
R is greater than equals to 0 but less than B, and B equals to NQ plus R.
Or B or A? B not equals to
A,
0.
A equals to BQ plus.
Yes, BQ plus R, where 0 less equals to R, less than, strictly less than B. Okay, this was the statement we have seen. But I would and here what is Q called? We call Q as quotient, and what do we call R? It is remainder, right? So this was the statement, and see here we have chosen A, B from natural numbers, right? So this division algorithm can be extended to the set of integers. That means where we can consider A, B not only in N but also be a integer which are not in N but in Z. That means A and B can be negative integers also. Okay, so what is the, that is the I mean we can extend division algorithm in the set of integers, not only in the set of natural numbers. So another form of or version of division algorithm, what it is, another version of division algorithm. This says if we take A and B from Z and B not equals to 0, then there exist unique integers Q and R belongs to Z, such that what can we say? Same form, A equals to QB plus R with 0 less equals to R, strictly less than mod B. See what are the difference here? So in previous case we have taken AB from natural numbers, and we have seen that R is this form. That means R is a positive integer such that 0 less equals to or less strictly less than b. And what if we extend this division algorithm to the set of integers, what will be the statement? We are taking ab from set of integers, not only from natural numbers, and b is non-zero as usual. Then we have this relation where r is a positive non-negative integer running from 0 up to mod b. So this is the difference between the previous version and this version. Okay, so we have seen the proof of division algorithm for this version, right, in our lectures. So here, using that proof, we will try to see how to prove this current version of division algorithm. Okay, let's see that. So what is the extra case here? Here in our first case we are taking b from n, that means b is a positive integer. Now here if we take let's say this is case 1, if b is greater than 0, then the proof is already same as the previous version, then the proof is done. So only case remaining is b is negative. So if b is negative, what does it mean? That means mod b, that is equals to minus b, and this is greater than 0. Now we will apply division algorithm for the integers a and minus b, okay, or a and mod b. So if we apply division algorithm for a and mod b, what we will get? Now apply division algorithm for a and mod b, then we get unique integers. Now see, so a belongs to z, but b belongs to mod b belongs to set of natural numbers. So if we apply this, then we will get unique integers q and r belongs to set of what should I say, a is greater than 0, let's say, okay, case 2 is, let's say, b less than 0, a greater than 0. Okay. So qr belongs to n, then such that a equals to mod b times q plus r with 0 less equals to r strictly less than mod b, because we are applying the division algorithm for a and mod b, and see here a is greater than 0. So from here what we will get? Mod b, since mod b was negative, mod b equals to minus b, so we are getting minus b q plus r, or say unique integers q prime, then q prime, write q prime here. Now let q equals to minus q prime, therefore from the previous statement what we are getting, therefore we get a equals to q b plus r such that 0 less equals to r less than mod b. So this is the statement we have written here, right? So when the case in a case 2, when b is greater than 0 and b is less than 0 and a is greater than 0, then we are getting this statement, right, using the previous version of division algorithm. Now what is the another case left? Case 3, a is less than 0 b is less than 0, right? So, and also there are case 4 which are very similar to the case 1. A is less than 0, b is greater than 0. So for these two cases, prove this case, or what I should say, proof of these two cases are very similar as of case 1. Okay, so since mod a less than 0 and since a less than 0 and b less than 0, you always can take mod a greater than 0, mod b greater than 0, and then apply division algorithm for mod a and mod b for case 3. And since in case 4 mod a less than 0, b greater than 0, then you apply division algorithm for mod a and b and proceed with the similar way as we have done in case 1. Okay, then you will find this kind of statement for case 3 and case 4 also. Okay, so you can do it by yourself, and since case 2 we have done already, now next move to some examples. So we can, how we describe this another version of division algorithm. Let's see it. So if we apply division algorithm for a equals to minus 61 and b equals to say minus 7, so what will be the question is, find q and r. Q means quotient and r means remainder. So how to find it? So what we have done in the proof, we have applied division algorithm for, so if a and b are negative, which one is negative, then apply division algorithm for their mod version. So that is what we have done in our proof. So first apply division algorithm between 61 and 7, then let's see how to adjust the sign of a and b. Okay, so we can write 61 as, if we apply division algorithm for 61 and 7, what we will get, what will be q and what will be r, what will be here, what should anyone, you can just tell me, and I mean, will anyone tell me, or are you following? Okay, so I am doing, so it will be 9 into 7 plus 2, not 2, sorry, that should be minus 9 if we apply. So minus 61 is a, and then just write it, minus 61 equals to, this remainder term should always be positive, 8 and 5. Okay, so there is some mistake from my side, that if you take so if you apply division, okay, let's write it again. 61 and for 61 and 7, if you apply, then you are getting 5. Okay, and if you apply between minus 61 and 7, see from case 1, we were applying division algorithm between a and mod b. I think here no need to consider these case. A less than 0 case, these are not needed because you can always apply division algorithm between a and b. If a is integer also, then also just try to find q can be from z, not only from r, and always keep in mind that this r will always lies between 0 up to b. Okay, this is the only thing we need. So if we want to apply division algorithm between some integer a which is negative and some integer b which is also negative, then no need to worry about the sign of the integer a. Just apply division algorithm between a and mod b, and then keep in mind that remainder should be positive and running between 0 up to mod b. Okay, so if you apply between 61 and 7, then you will get this one. But if you apply division algorithm between minus 61 and 7, then keep in mind remainder should be positive. Then in this case, what will be q and what will be r? If you multiply here by 8, if you write here 8 into 7, then you are getting, this is 56. But to get 61, you have to add minus 5, right? But remainder r cannot be negative in for any case. So remainder should always be positive. Therefore, we cannot multiply by 8 here. We have to multiply by so to get positive remainder, what should I multiply? Not
Minus
by
9.
8 but by minus 9 into 8 plus, what will be remainder then? Sorry, this is 7 plus 2, right? And 2, see, 2 is lying between 0 up to mod of minus 7, that is mod of b. So what will be therefore what we can write here is, then q will be minus 9 and r will be 2 only. Okay, let's try another example. Say example a equals to 57, b equals to minus 5. Then just tell me the, compute by yourself and tell me the answer. What will be q and r? What shall we write here and what shall we write here? Keep in mind this term will always be positive. Okay. So you are saying 12 and 3.
Minus 12.
So think once
Minus
again.
12.
Think once again. If you write say minus 12 into minus 5, or then what you are getting? This is 60. But then what you have to write in this case? R. This number is 57, right? 57, not 67. So then you have to write minus 3 here, otherwise you will not get 57. So again think and just tell me. This r should be positive. apply division algorithm between 57 and mod 5. So if you apply division algorithm between 57 and mod 5, then what should be q? 11, right? And then just this is exactly the case q2, case 2, this case. Here apply division algorithm between a and mod b, then get q prime. Then what will be q here? Q is just minus q prime. So in this example, apply division algorithm between 57 and mod b, that means 5. Then write q as minus of q prime. So what will be q prime here? Q prime should be 11 here, and then write q as minus q prime. So this number is, equals to 55. Then we have to add plus 2, right? So here we should write 2. So what is the answer then? Therefore q equals to minus 11 and r equals to 2. So these are two examples when a is negative, when a and b both are negative, and this case when a is negative and a is positive and b is negative. So in this case, just apply division algorithm between a and mod b, write then get q prime, write q as minus q prime, then you will get what are the quotient and remainder. Okay. And for the previous case where both of them are negative, then apply division algorithm between minus 61 and 7 and try to keep the remainder r between 0 up to 6. So if you always keep in mind that r should be positive and less than mod b, then you can easily get the value of q and r. These are some typical type of examples which you will see in your assignment 1, I think, and I hope you already have solved these kind of questions. So now let's see some application of division algorithm. Okay. So some observation you can say. For any given integer, n belongs to n, we can write any integer in one of the following form. Or any say, okay, natural number, following form. What are they? mq or mq plus 1 or mq plus 2, mq plus m minus 1. Okay. For some q belongs to n union 0. So can you tell me why we can write these as you are given some integer, some fixed integer, some fixed natural number m, then I am saying that any integer, if you give me any integer, then we can write that integer in one of these forms. We can write it as mq or mq plus 1 or mq plus 2 up to mq plus m minus 1. What does it say? Let's see some example. Let's say we are I have given you m equals to say 8. Just tell me any integer and I will I confirm you that we can write that integer either of the form 8q or 8q plus 1 or 8q plus 2 or something between 8q plus 7. This is an application of division algorithm. So what we have seen from division algorithm, that if we divide any integer by some another integer, the remainder some another integer b, the remainder should lie from 0 up to mod b. So if we divide any integer by 8, what are the possible cases of remainder in this case? So I am saying, if we divide any integer by 8, then the set of possible remainders is, what is the set? If we divide any integer by 8, what will be the value of I mean what are the remainders we may get by division algorithm?
Zero up to 7.
0 up to 7. So 0 or 1 or up to 7. These are the possible cases of remainder. So divide any integer when we are getting remainder 0, that means remainder 0 means we are writing that integer as multiple of 8. When we are getting remainder 1, then what will be the form of that integer? Multiple of 8 plus 1. When the remainder is 2, then what is the form of that integer? Multiple of 8 plus 2. In this way, we can write any integer of the form some 8k plus 1. Some 8k plus r, where r is lying between 0 up to 7. Okay. So this is one observation. So if I tell you that okay, we will see some problems, then we can understand why we have written this observation. Okay, when we will solve some problems, then we can get some idea why this is very important observation. Okay, so the what we have just seen, that apply division algorithm and remainder is 0 up to mod b. So very particular or special case, when the remainder is 0, what do we call in that case? Say we are applying division algorithm between a and b, and in this case we are getting remainder is 0. Then what we can say here? Apply division algorithm between a and b, that means divide a by b, and if I say that you are getting remainder 0, what do we call this case? B is dividing a, right? So if we apply division algorithm between a and b, and special case is remainder is 0, then we say b divides a. Okay, so here I should write apply comparison algorithm between A and B, and remainder is 0. If I say it, then we can say B is dividing A. That means we can write A of the form BQ for some Q belongs to Z, right? So then we call the then we say talk about divisibility and GCD and all these things. So let's solve one question. So if I tell you, so that square of any integer is of the form 3k or 3k plus 1. So what this question is saying? This is saying that any integer, take any integer, then square it. Then this square has the form either 3k or 3k plus 1. So can any ma'am, like the way we extend division algorithm to integers can be notions of primes to integers? No. In number theory, whenever we are talking about primes, then we are talking about only about the natural numbers. Okay, in number theory we don't talk about the primes concept for total integers. You can say that some negative integer has like -4. -4 equals to 2 into -2. So -4 is divisible by -2 or 2. But we don't talk about prime concept for the set of negative integers. Okay. So someone was saying that whether you were saying in the first, right, algebraic number theory, yeah. So this prime concept, it is not bounded in number theory only. If you further study about ring theory, ring field theory, then also you will get some generalized concept of prime, but in number theory we don't generalize this concept of prime for the set of negative integers. Okay. Is your doubt clear, Jose?
Yes, ma'am.
Okay. Now concentrate in this question. Will anyone try to tell me how to proceed with this question? What this question is saying? This is saying let A belongs to Z be any integer. Okay. Then it is saying A square has the form want to show. Short, in short I am writing WTS. A square has one of the forms 3k or 3k plus 1 for some k belongs to Z. Okay, this is the thing what we have to show. Now we have just sometimes ago we have seen this observation. Here what I was saying that given any integer m, we can write some other integers in one of these forms, right? So we will see the application of this observation in this question. So this is saying that A square has the form 3k or 3k plus 1. So since the form is expecting in terms of 3 times k or 3 times k plus 1, what should be our natural guess to consider the form of A? So naturally, so this is the intuition what form of A we should consider. Since here in this question it is asking about the form multiples of 3 or 3k plus 1, so we should have the intuition that A can be written in one of the following form. We can write A as 3k or A as 3, or we say here we are using 3m plus 1, or A can be written as 3m plus 2. So this is the observation. So I am saying that you are given the natural number 3, write A in some form like either 3m or 3m plus 1 or 3m plus 2. We can write A in this way because while we are dividing any integer by 3, we can get remainder only 0, 1 or 2. That's why A has one of these 3 forms. So when A has the form 3m, what will be A square? That is 9m square. That means 3 into 3m square. So in this case A has the form, which form? 3k, right? This is again an integer 3m square. Therefore when A has the form 3m, then we have A square has the form 3k for some integer k. Now let's concentrate on this case when A equals to 3m plus 1. In this case what will be A square? That is 9m square plus 6m plus 1. So we can write it as 3 some k prime plus 1, where k prime is some integer you can calculate, that is exactly equals to 3m plus 2 3m square plus 2m. This k prime equals to. So when A has the form 3m plus 1, we can write A square of the form 3k plus 1. And when A has the form 3m plus 2, in this case what will be form of A square? A square equals to 9m square plus 12m plus 4. That means 3 into 3m square plus 4m plus 1 plus 1, that is, so I should write it somewhere else. Okay, I am erasing it and writing it in the next page. So when A has the form 3m plus 2, then A square equals to 9m square plus 12m plus 4. We can write it as 3 into 3m square plus 4m plus 1 and plus 1. So this is of the form 3k some double prime say, where k double prime is also an integer, and sorry, this is 1. Okay, so in any case when so A has one of these form, either 3m or 3m plus 1 or 3m plus 2. In any case, see, we can write A square as either 3k or 3k plus 1, or in this case also it is 3k plus 1. So this is the this is what it was asking in this question, that square of any integer has the form either 3k or 3k plus 1. So do you have any doubt in this question or any query where you didn't understand? or why I have what is the intuition of considering A in one of these three forms, 3m or 3m plus 1 or 3m plus 2. So you can you understand, right, that any integer can have one of these form, 3m or 3m plus 1 or 3m plus 2. Any doubt in this conception? Anyone has any doubt in this proof or something? This is the very typical type of questions which you can get in number theory, I mean in any course of number theory. Okay, so let's so I hope it is clear to all of you. Let's try some another question. Okay. Now similar kind of question, it is asking to show that a into a square plus 2 upon 3, this is an integer for all a greater equals to 1. Okay, so what this question is asking, this is asking given any integer a greater equals to 1, so that a into a square plus 2 by 3 is an integer. So in other words, a into a square plus 2 is divisible by 3. So if a into a square plus 2 is divisible by 3, then only we can have a into a square plus 2 by 3 an integer, otherwise it is not possible. So what we want to show? Want to show that a for all a greater equals to 1, a into a square plus 2 is divisible by 3. This is the case what we want to show. So again we can consider three cases here. So a has one of the form either 3m or 3m plus 1 or 3m plus 2. So let's say case 1. Case 1 is a has the form, let a has the form a equals to 3k, that is a is multiple of 3. So in this case, what is a times a square plus 2? This is exactly equals to, or by 3 if you say, no, let's start with, okay. This has the form 3k into 9k square plus 2, and this is multiple of 3, right, because 3 times k into 9k square plus 2 and k into 9k square plus 2 is an integer. Therefore when a has the form 3k, a into a square plus 2 is divisible by 3, equals to 3k prime say. So in this case we are done. So okay, let's write this case a into a square plus 2 by 3 is an integer. What is the second case? Let a has the form 3k plus 1. Okay, so when a equals to 3k plus 1, for some k belongs to z, what will be a into a square plus 2? This is equals to 3k plus 1 into a square means 9k square plus 6k plus 1 plus 2, that means 3. So we can write it as 3 times 3k plus 1 into 3k square plus 2k plus 1. Again this belongs to z, so in this case also a into a square by 2 a square plus 2 by 3 is an integer. What is the remaining case? Case 3 is let a is of the form 3k plus 2 for some k belongs to z. In this case also you can see a into a square plus 2 will have the form 12k plus 4, that means sorry, not 4 plus 6. So this is again we can write some k prime. For k prime belongs to z, you can calculate what is the k prime and you can see it is belonging to z only. So in this case also, here also a into a square plus 2 by 3 is an integer. This is very similar kind of question what we have done previously. So now let's so these are, I hope you can solve the problems given in assignment which are very similar to this kind of question. Now let's move to the to some observations from the topic GCD. Okay, so anyone has any doubt till now or any questions regarding those topics? So if not, let's go to another observations. So here we solve it. So I will try to point out some observations from the lectures. So what we have seen in GCD, can you recall what is the definition of GCD? GCD of AB, we denote it by first bracket A comma B. This is let's say this is equals to D. What is the definition of GCD? D, there were two conditions, D divides A and D divides B. The second condition is crucial, if some another number E divides A and E divides B, then E
divides D. E divides
E divides D or D divides C?
because D is the
greatest common integer, a common divisor. So in the proof of GC of existence and uniqueness, what you have seen, what is the form of D? Can you tell me? It was
linear combination of A and B.
Linear combination of A and B. D has we can write D as some A alpha plus B beta for some alpha beta belongs to Z, right? Now tell me, there in that proof we have constructed some set and D was some element of that set. So can you recall what was the set we have constructed in that proof? So can you remember, we were considering some set like T or X, I cannot remember what, let's say T. so I hope you can recall. We were considering some set T, like which was containing those kind of natural numbers ax plus by, such that xy belongs to z. We were considering that set, and we were telling that d, I mean the in proof of that existence, we are considering d is the least element of T, right?
Ma'am, I up and down.
Yeah, tell me.
Ma'am, how can we claim that T has a minimal element?
I am not claiming. I am saying that it is already shown in that lectures. So if you
It is shown in the lecture that T will have a minimal element.
T will have minimal element, and okay, it not shown? Okay, let's show it then. Okay, let me see that lectures. No, it was defined. Just go through the lectures again. It was defined that I mean, I can show it also, but we have constructed in that proof. We have set that D to be least element of. It was written as x, not T. Okay. So if you can, so what we have done in that proof is that we have constructed this set x, and we have taken, what we have taken, we have defined D to be least element of x. Then what we have done, we have shown that if E divides A, E divides B, then E divides it has already gone. We have defined D to be A alpha plus B beta, be the least element of x. And then what we have shown, that if E divides A, E divides B, then E divides D. How we have shown this one? This one exactly use the least element of x. So we can recall it again. Okay, so if E divides A and E divides B, then we can always say E divides A alpha plus B beta, and that is equals to D. And how to show that? How to show that D divides A and D divides B? To show this, we are applying division algorithm between A and D. Okay, so apply division algo between A and D. So what you will get, A equals to QD plus R, and what is R? 0 less equals to R, strictly less than D. And what we have shown, then we can get R has the form A minus QD. And a minus qd, and now see here we have set d equals to this one, right? So we can, if we replace the value of d, we what we will get, q a alpha minus q b beta, right? And so we can write it as a times 1 minus q alpha plus b times minus q beta. Now see, this r is again in this set t, because this is an integer and this is also an integer, and we have constructed t to be x to be this set. So this is x. And now what is the contradiction here? Here we are getting some contradiction, because we have constructed, we have set or defined d to be of this form and to be least element of x. Since r is strictly less than d and r is also belonging to the set x, this is the contradiction, that d is the least element of that set. So this is a contradiction, and that's why we have r equals to 0. That is the proof I was recalling. I mean, to show that some d exists, and to show that d is unique, or like that, or d satisfies those two conditions, that means d divides a and d divides b. So for showing this step, that d divides a and d divides b, we use this language, that d is an element of the form a alpha plus b beta, such that this is the least element of the constructed set x. So now do you get how we have, how it was proved in that lecture? Can you recall now? So Jose, you were asking, right?
Yes, ma'am.
So can you recall, or do you still have doubt?
Actually, I was saying, ma'am, how can we say that the least element will exist for the set x that you defined to be capital D?
Okay. That is by the well ordering property of set of natural number. Okay, that was your question. So what is the well ordering property of set of natural numbers says? It says that every non-empty subset of natural numbers has a least element. Now see here, x, this is the set, how we have defined it, of this form ax plus by, which are in natural numbers, right? So this set x is a subset of set of natural numbers, therefore it will follow the well ordering property, and therefore some least element of x will exist. Okay, so that's why this kind of d exists. Is it clear now?
Okay, thank you, ma'am.
Okay, so this was the proof.
Ma'am, can you share the recordings of this session, ma'am?
Yes, it is already shared. It is shared in your NPTEL website.
Okay, ma'am. Thank you.
So now what I want to point out here is that d is d is not only the least element, every element of this set x will be multiple of d. Okay, so what is the observation here I want to add is that, so we know what is that set x. If what I want to, okay, the set x contains all the multiples of d. Okay, so how to prove it? What does it mean? So it means we have to show that one, we have to show that d divides ax plus by for all ax plus by belongs to x, and another thing we have to show that if n times d, that means any multiple of d that belongs to that set x for all n belongs to z. So what this statement is saying, the set x what we have defined earlier, this contains all multiples of d. I mean, you take any element from this set x, you have to show that that is a multiple of d. In other ways, if you say nd is a multiple of d, then nd will belongs to that set x for any n belongs to z. So this is the two conditions. I mean, this condition is saying take any element from the set x that will be a multiple of d, that means that will divide d. I mean, d is divisible by d divides this element, and conversely any multiple of d that will belongs to the set. If we can show these two conditions, then we can say x will contain all the multiples of d. So let's see the proof. So now we know that to prove we know that d divides, d was GCD of AB, d is the GCD of AB, or we can, according to our notation, d equals to AB. Okay, so d divides A and d divides B. This will imply d divides ax plus by for all ax plus by belongs to x. This is the first condition. So we have shown. Now what is the remaining? Now take any multiple of d and so that will have the form ax plus by. Now to prove this condition, what we can check is that okay, so d GCD of AB and d has the form a alpha plus b beta. This was the form of d we have considered, and that was the least element. And nd means n times, n a alpha plus n b beta, that is again belonging to x, because this belongs to n, and according to the definition of n, this element, you can write it as a times n alpha plus b times n beta. So this n alpha, n beta, these are belonging to z, and nd, this is already belonging to set of natural numbers. Therefore we can say this set x will contain all the multiples of d. Okay, so one thing I need to, what was x? Okay, that belongs to z. So that should be n belongs to n, positive multiples, not z. Because if we consider z, then nd can be negative also, and in our construction of the set x, negative elements does not belongs to X, therefore we have to consider belongs to N. Okay, all the positive multiples of D. So this is one beautiful observation. I mean, we can particularly see what will be the elements of that set X. Okay, and let's try some another corollary or theorem, you can say, not theorem exactly, corollary. So let D equals to GCD of AB. Can we construct some element, I mean some relatively prime element using this A, B and D? So if this is the question, then we can answer that yes, we can construct some elements from these given integers A, B and D such that they are relatively prime. So first, okay, let's write it. So do you know what is the definition of relatively, what is the statement, I mean relatively prime? When we call relatively prime? Do you know when we call that two integers are relatively prime?
If GCD is 1.
If GCD of A and B, this is 1, then we say that A and B are relatively prime. So if GCD of AB equals to 1, then we say A and B are relatively prime. Okay, so now this is the question, so that if GCD of AB equals to D, then GCD of A by D, B by D, that is 1. That means A by B and A by D and B by D, they are relatively prime. Can you show?
Ma'am, we can write in linear combination and divide by D.
Yes, exactly. So we have, since D is the GCD of AB, we have seen that D has the form A alpha plus B beta for some alpha beta belongs to Z, and D divides A, D divides B. So if D divides A and D divides B, then A by, this implies A by D, B by D are integers, and from this expression what we can write, 1 equals to A by D times alpha plus B by D times beta. Since this is an integer and this is also an integer, so what we can say, and 1 can be written in these linear combinations, then we can say therefore GCD of A by D, B by D, this is exactly equals to 1. Okay. Now another comment I want to add in this previous observation. So we know that D has the form A alpha plus B beta, but can you tell me whether this is a unique representation? Do you?
Yes, ma'am. Ma'am, because alpha, ma'am, the least element is also unique.
Least element is unique, that's fine, but I am asking whether the form of D, I mean alpha beta, D equals to A alpha plus B beta. So I am asking whether alpha beta, this tuple, this is unique or not. What is your guess? So I want to give you a hint. So A alpha plus B beta D equals to this. So can you represent it in R2 plane by some line or anything? So say this is the line for A, this is line for B. I mean x axis, y axis, I am renaming it as A and B. So D equals to A alpha plus B beta, what does it represent? This is some straight line, say
Not passing through origin.
not passing through origin. If it passes through origin, then D should be 0. So that should be some line. It can be in this form, or it can be in this form, or it can be in this form, or it can be, or how should I write?
Ma'am,
This form, yes.
while we were trying to prove that D is the GCD, we showed that it is the least element of that set.
Yes.
So, ma'am, in that set, if the least element is existing, ma'am, those alpha and beta must be unique.
Least element is unique. That
For the
there is
existence of
no
least
doubt.
element, ma'am, because
Yes.
that is equals to GCD.
Yes, but least element is always unique because the set is natural numbers and it is well ordered set. There is no doubt. But can't you get that D equals to A alpha plus B beta and A alpha prime plus B beta prime? Can't you get that? I am giving you this hint. So just think, and if you get any answer, just tell me in next class, okay? Because that's I am saying that the answer is no, that is not unique. You can get some another integers alpha beta, alpha prime beta prime, such that D will be alpha. I mean, because if you just say that,
Ma'am, if they are, ma'am, if it not zero, then they are multiples of each other.
yes, there D is not 0 because GCD cannot be 0 other until A or B any, so I mean they are non-zero. What shall I say? D is some non-zero integer say. Then I am asking whether that pair is unique. I mean alpha beta, whether this pair is unique or not. And if you say that or guess that it is unique, then just tell me the reason in next class. Or if you say that that is not unique, then also tell me why are you not why you are saying that not unique. That is just basic fact, and you just check with some several examples and you will find that it is not unique, and try to find out the reason. And I am giving you hint of this graph, okay? So I will not say it because this is some basic information you should know, and if you can get, I will tell you in next class, okay? So these are the observations I have prepared, and so next let's see what are the topics we tried to cover. So we have done this one, this observation 1 and 2. Now I will solve some examples from prime numbers and fundamental theorem of arithmetic, then some problems from congruence relation, okay? So okay, this is our first questions. Let P be a prime. you know the definition of prime, and you have seen several examples of prime, several what will be the form of primes and all, like that you have do you see the lectures that there are infinitely many primes of the form 4n plus 1 or 4n plus 3, or more general form, that Dirichlet formula. So you have seen all these, right? So this question is not exactly related to those results, but very similar to those kind of results. Okay, let P be a prime and P divides a power n for some integer a, then so that P power n divides a power n. So can you tell me, this will I mean, to prove this one we will need some basic properties or basic theorems of prime numbers, what we have seen in our lectures, I mean in first week content. Can anyone tell me? So what is
P will divide A, ma'am. P will, so either A has to be equals to
given? Then what can we say?
P divides A or A power n minus 1.
P divides, because we can write a power n as a times a power n minus 1. Then using then what, by which theorem we can conclude this one? Using
Euclid's lemma.
Euclid's lemma. We can say that P divides A. So P divides A or P divides A power n minus 1. Then again use Euclid's lemma for P divides A power n minus 1. So in this way, ultimately after finite step or after n many steps, you will see that P divides A. Okay, because A power n has the only factors A times A times A n times. So using Euclid's lemma repeatedly, we can conclude ultimately that P divides A. So if P divides A, then P equals to AK for some k belongs to Z, and then P power n equals to A power n times k power n. We are saying k prime it, where k prime equals to k power n. So this implies P power n divides, oh sorry, I have written it in the P divides A, that means A equals to pk. So A power n equals to P power k, P power n times k power n, we are saying it k prime. So this implies P power n divides A power n. Okay, this was the basic result. Now let's try another question. So no doubt, right? Okay, that was very basic. So next question is, so that any prime of the form 3k or 3n plus 1 is also of the form 6m plus 1. What does it say? Let's say P is some prime which is equals to 3n plus 1. Then so that this P we can write it as 6m plus 1 for some different integer m. Okay, so can you tell me, anyone, how to proceed with this question? So given that equals to 3n plus 1 for some n belongs to z. We have to write p as 6m plus 1 for some integer m. So I have used the similar technique I am going to use in some previous questions, and I have written it as observation. So can you guess how should we proceed further?
Use division algorithm for n and 6.
Yes, you can use division algorithm for 6, but 6 is some big number. So I mean big number in the sense that you have to consider total 6 cases when remainder is 0, 1, 2, 3, 4 and 5. So we don't have to use that much those many cases. If we consider division algorithm by 2, that's enough for this case. So let's see. So n can have, since n belongs to z, n can be odd or n can be even. So case 1, let n equals to 2k, and some case 2 we will consider n equals to 2k plus 1. Okay, so when n equals to 2k, p equals to 6k plus 1, right? Hmm. 6k plus 1. So this is the exact form we were needing. Now when n equals to 2k plus 1, what is p? P equals to 3 times 2k plus 1 plus 1, that means 6k plus 6k plus 3 plus 1, that means 6k plus 4. Okay. Okay, so now tell me, if n equals to 2k plus 1, then p equals to 6k plus 4. Is 6k plus 4 a prime number, can be a prime number? My question is, when n is even integer, then we have p has the exact form 6k plus 1. But if n is odd integer, then can we have p of the form 3n plus 1 if n is odd? That is my question. So if n is odd, that means if n has the form 2k plus 1, we are getting that with the given condition n is of the form 3n plus 1, we are getting that p equals to 6k plus 4. But 6k plus 4 equals to 2 times 3k plus 2. So that is always a composite number, cannot be a prime number, because 3k plus 2, since k has to belongs to some z or like that, then otherwise p cannot be any prime number if this is not equals to 1. Okay, so therefore we can say okay, so let me write, then p cannot be a prime unless 3k plus 2 equals to 1, because if 3k plus 2 is not 1, then that will always be a composite number, that means 2 times some another integer, and that means that is k equals to minus 1/3. But here we were taking k to be a integer, so k can never be minus 1/3. since k belongs to Z, it is we can conclude that P cannot be of the form 3n plus 1 if n is odd number. So therefore if P is a prime of the form 3n plus 1, then n is always even and P can be written in the form 6m plus 1. So what I wanted to show here is that it is given P equals to 3n plus 1. Now my question is, if n is even integer and n is odd integer, in these two cases can P always be a prime? We have seen that if n is even integer, then if n is even integer, then P has the form 6k plus 1, what it was expecting in this question. But if n is odd integer, then it cannot be the case that P has the form 3n plus 1 and P is a prime, because considering this n equals to odd case, we are getting P equals to 2 times 3k plus 2. Now since P is a prime, then 2 times some integer which is not equals to 1 or minus 1 cannot be a prime number. So only possible case is 3k plus 2 has to be 1, but 3k plus 2 cannot be 1 in any cases when k is belonging to Z. Okay, that's why we are saying that if P has the form 3n plus 1 and P is a prime number, then n has to be even integer. Okay, and in this case we can write P as of the form 6m plus 1. So this is the only case when P can be prime and P has the form 3n plus 1. But if n is odd integer, then we cannot have these simultaneous two cases, that is P is prime and P has the form 3n plus 1. So do you get it what I have tried to show? Any doubt in this language? Okay, so this was one nice question or observation, you can say. Another question I want to add here is that, so I was saying some definition of composite number. So composite number, definition of composite number I should recall. Okay, let's recall the definition of composite number first. So DE. So we call or we say n to be a composite number if n, we can write n as the form a times b such that 1 strictly less than a less equals to b less than a. Okay, So if we can write n to be product of two integers which are greater than a and less than n, then we can say n to be a composite number. For example, 4, 6, 2 into 2, 3 into, 2 into 3, like that, 9, 10, 2 into 5. These are all composite number. And another similar definition is perfect square. What is the definition of perfect square? We say n to be a perfect square if we can write n equals to a square for some integer 1 less than a less than a. Okay, so these are two definitions. So next question we want to see will involve the definition of perfect square. So the question is, the only prime p for which 3p plus 1 is a perfect square is, so let's fill in the blank. Okay, what should I write here? So it is saying that the only prime p which is the form 3p plus 1 and this 3p plus 1 is a perfect square.
5.
Okay, so you are saying 5. So can you tell me the reason?
It is 16. It is equal to 4 square.
So you have just, but the question is saying this is the only prime. Can you tell me that? You have got one, but since I was giving you that only prime, that's why you have filled the blank, fill in the blank. But if I tell you that, so that the question is, so that the only prime p for which 3p plus 1 is a perfect square is 5. I am not giving you the question, fill the blank. I am saying you to prove it. Then what will be your answer? Okay.
It will not be a prime number, it will be a composite number.
I am saying that it is a perfect square. I am not saying 3p plus 1 is a prime number. I am saying p is a prime such that 3p plus 1 is a perfect square. That is the given condition. So let's see. So your guess is right. Exactly, this is the prime number p equals to 5 for which 3p plus 1 is a perfect square. And to show the uniqueness, I mean that is the only prime, let's see how to answer it. So it is saying that a given condition is p is prime and another condition is 3p plus 1 is a perfect square. Perfect square means 3p plus 1 equals to a square for some a belongs to z. This gives us 3p equals to a square minus 1. Now a square minus 1 equals to a plus 1 into a minus 1. We can decompose it in this way. Now from here we are getting p equals to 1/3 of a plus 1 into a minus 1. Now given condition is p is a prime, so this number has to be an integer. That means 3 has to divide either a plus 1 or a minus 1. And not only that, since p is a prime, if 3 divides a plus 1, then the other term, a minus 1 or a plus 1 by 3, that should be a 1. So what is my claim is, since p is a prime, so that cannot be a composite number. That means one of these two numbers has to be 1. So okay, so p has first see when a plus 1 or a minus 1 is divisible by 3. Okay, in which cases? Now a is an integer, so we can have the form of a either 3m or 3m plus 1 or 3m plus 2. Let's consider 3 cases here. First case 1, consider a equals to 3k. In this case, what is the form of p? 1/3 3k plus 1 into 3k minus 1. Now 3 cannot divide 3k plus 1, also 3 cannot divide 3k minus 1. Therefore in this case, a cannot have the form 3k, because p has to be integer first, right? Because p is a prime, p is a prime, and before prime it is an integer. So this right hand side should be an integer. That means 3 should divide any one of 3k plus 1 or 3k minus 1, but 3 cannot divide any of these two form. Therefore a cannot have the form 3k. So what is the conclusion here? Since 3 cannot divide 3k plus 1 or 3k minus 1, so a cannot have the form 3k. So first case is discarded. Case 2 is a has the form 3k, let a equals to 3k plus 1. In this case, what is p? 1/3 of 3k plus 2 into 3k, that means 3k plus 2 into k, right? Yes. Now so here p is an integer, it is okay, but another condition is p has to be prime. Therefore either 3k plus 2 or k, that should be 1. So since p is a prime, we have two choices, either k equals to 1 or k equals to or 3k plus 2 equals to 1, right? So if k equals to 1, then 3k plus 2 equals to 5, that is p equals to 5. So is a prime. So therefore when k equals to 1, this p will be a prime number. And what is that prime number? P is exactly the prime 5. But when 3k plus, whether 3k plus 2 can be 1 anytime, because k is an integer. What should I write here? But 3k plus 2 cannot be 1 for any integer k. Therefore, only possible case is p equals to 5. In this case 2, and in case 3, that is let a has the form 3k plus 2. So in this case, what can we say? P will have the form, if you divide by 3, and you will see that it is of the form 3k plus 1 into k plus 1. Since again, so right hand side is a integer, it's okay, but another condition is p has to be a prime. Therefore, since p is a prime, with the similar argument we have done in case 2, what we have to get, since p is a prime, either 3k plus 1 equals to 1 or k plus 1, this is equals to 1. So that means k equals to 0. So if 3k plus 1 equals to 1, then also k is 0, and if k plus 1 equals to 1, then also k equals to 0. But if k equals to 0, then what is the form of p? From this this say 1, then p, then by 1, then by 1 we have p equals to 1, which is a contradiction because 1 is not a prime. So therefore, in all these 3 cases, what is the only possibility of the prime? Only possibility of the prime is p equals to 5. So let's so see from the first cases what we have done. We have shown that from the given condition 3p plus 1 is a perfect square. From this given condition we can rewrite p as 1/3 of a plus 1 into a minus 1. Now a is an integer, so a can have 3 forms, either a equals to 3k or 3k plus 1 or 3k plus 2. Now analyze what can be the value of p in all these 3 cases separately. So for case 1, that is when a has the form 3k, we are finding that p has this form, but in this case this right hand side cannot be an integer for any k belongs to z. Therefore we cannot get any prime p such that a has this form 3k. So this case 1 is discarded. From this case 1 we are not getting any p satisfying the given condition. Now we have tried to show the case when a equals to 3k plus 1. In this case we are finding that p this right hand side is an integer, so it's okay. Now another condition is p has to be prime. So if p is a prime, then either k equals to 1 or 3k plus 2 equals to 1. But see, 3k plus 2 cannot be 1 for any integer k. Therefore what is the conclusion? Only possible case is k equals to 1. Now if you put k equals to 1, from this equality you are getting p equals to 5. So p is satisfying all the given condition. P is 5, p is 5 and 3p plus 1, that is a perfect square. So in this case 2 we are getting 1 prime, that is 5. Now in case 3, when A has the form 3k plus 2, can we get any prime P such that 3p plus 1 that is a perfect square? The answer is no, because satisfying the given condition we are getting k equals to 0, but if k equals to 0, by this expression P has to be 1, but 1 is not a prime. Therefore from this case 3 also we are not getting any prime. Okay, therefore what we can conclude is P equals to 5 is the only prime which are satisfying the given conditions of the question. So that's how we have shown the only prime with the possible condition with the given condition is 5. Is it clear?
Yes, ma'am.
So if the question was a numerical type question, just fill in the blank, then you can guess easily and that will be mark 1 question. But if this is subjective type question and if it asks you to show that there exists only 1 prime with the following conditions satisfied, then you have to you have to prove in this way. Okay. So I was having some other questions, but let's because the time is already over, I would like to take your 15 minutes more to cover the last portion. Okay, because these will be useful to solve the week 2 assignment. And since my first week 1 tutorial session was only of 1 hour, so I couldn't get the time to solve solve the problems from primes and GCD and all. So that's why it is taking some extra time. So do you have any problem, or shall I stop here and we can discuss in our next tutorial class? What should I do? So
Next class.
next class. Okay, so let's stop then. And I have to remove the okay. So what we have done is we have done up to this 3, right, not this 4. So let's remove it for now, because we will try to cover it in our next class. Okay. So anyone has any doubt what I have shown, or some other questions related, not related to today's discussion? So if not, then let us stop here today. And if you have any questions from this from today's discussion, you can ask me in next class. Okay, I am ending the session.
Thank you, ma'am.
D equals to ax plus by is a linear Diophantine equation, and hence infinite number of values of combinations of x and y are possible. Yes, you are right. But I think so if you know the concept of linear Diophantine equation, then you can argue with this argument. But without knowing that definition or that term, from the graph I have shown you that it will have several infinitely many integer values. So all those integer values will give us some pair. Okay, so that's why it will have infinitely many possibility of those pairs alpha beta. So So you are also right. That is the exact reason.
Ma'am, then alpha beta are not unique.
Not unique. Yes. And you can try some examples by yourself. Just take any two integers and write d of the linear combination of those integers, and try to get some different tuple alpha beta, such that d can be written as a alpha plus b beta. You can try
Ma'am,
with some small examples also.
ma'am, while sir was, in the lectures also, sir has given, only two examples how to write the linear combination. Like once he was doing back substitution, and in other example he showed without back substitution. So in the next class, ma'am, whenever you are doing it, try to cover those examples as well.
Okay, so I mean, do you have doubt how to get that by back calculation or using some trick?
Ma'am, I can do it by back calculation, ma'am, just by substituting the values I can get.
Yes.
If
Then
it is not unique, then there are other methods as well, like.
okay, so you can try with the exact examples I have shown. I mean, in one example, sir have used some trick like multiplied by 10 and then try to find out that values of alpha beta. Now, if you try that example by back by substitution method from that division algorithm steps, then you can get just apply that back calculation and you will get different alpha beta for that example itself.
Okay.
So if you don't get, then in next class I will just ask you, and if you don't get, I will write it down. Okay.
Okay, ma'am.
Okay, let's stop. Bye bye.